Okay, guys. So this is a very simple introduction to how NMR spectrometer works. It is intended for project students. It's very kind of low level, and what I wanted to do, if I manage to, is to build an NMR spectrometer together with you today. So the idea is always linked to the physics of what we want to do. And as in any other spectroscopy, what we are going to do is just to make a transition between two energy levels. Okay, so we are going to have like two energy levels, I and J. And what we have to do is to drive the transition between these two levels. So doing this kind of transition. And therefore we have to and this, we know that the difference between two levels is always, it can always be written as the Planck constant times the frequency. Okay, so once we find out how big is this, we know which kind of frequency we have to use. With NMR there is a small issue which to begin with, and is that if you don't have any magnetic field, all the spin energy levels, they are all degenerate. So actually in the absence of field, so if we have no field, these two energy levels, which may represent, for example, the two energy level of an isolated proton, they are degenerate. It's only when we have a field that actually they split in this. So the first thing to be able to do a spectroscopy is actually to split these two levels. That's why we need a magnet, which generates a magnetic field. So this is the first piece we have to put together. So we have to go and buy an NMR magnet, which usually looks like this. Okay, it's a can, and it's not that great actually. So let's not complicate it too much. Usually stands on feet. Okay, and there is a hole here and a hole here. And and this is the magnet. And what it does is basically just generating the field which we need to split these energy levels. Okay? So how we do, what are the possibilities to have a magnet? There are at least three different possibilities. One thing is that there are natural magnets in nature. So there are materials which are magnetic, and therefore they generate a magnetic field. And then you can just buy one of those things and generate a magnet. And put your sample next to it, and then you get the splitting you want. However, this is a good solution. In fact, the first NMR instruments were done like that. But there are some technical limitations, so it is very difficult to exceed the 2 Tesla limit. And nowadays they sell instruments which have 23, 24 Tesla. So it's very, I mean, it's an order of magnitude less than what we could do today with other kind of magnets. A different solution could be like to use electricity, because we know that from Maxwell's law, we can generate a magnetic field by passing a current through a coil. So the simplest thing you can have a coil, you can have a voltage generator, so a battery, and therefore induce a current into the coil, which induce a magnetic field. So these are known as resistive magnets or electromagnets, and they are also very, you can buy those things. Again, there's a big problem there. You need a lot of current, so they are very expensive to maintain, because once you get the field, you would like to keep the field very stable to keep this field, these levels at the same splitting. So you need very good stability of the field, and then you want it on, basically as long as the experiments run, or possibly always on, and this will consume a lot of energy. So there is a third solution, which came out from the concept of superconducting materials. So there is a class of material which are called superconductors, and they are called as such because they have no, because in some conditions they have no resistivity. So one of the problems with resistive magnets or with electromagnets is that once you put the current through the coil, then you have something which is called Joule heating. So you actually start losing your power as heat. Okay, and this actually goes. So the Joule heating, let's call it, I don't know, delta J or whatever. This actually is the square of the current times the resistance. So since the coil will have a resistance, and since you are passing through a current, you are losing a lot through this equation. Okay. So what are the alternative? If there are materials which have no intrinsic resistivity, so there is no resistance, then you don't have this effect. So the current will stay. Once you put the current there, it will stay forever. The only issue with that is that this material, to be superconducting, they have to stay cold, and they usually show this superconductivity at very low temperature, of the order of a few Kelvin, or maybe a few tenths of Kelvin in the best cases. Okay, so in particular, however, if you can keep the coil cold, okay, the coil became a superconductor, and then you put a current one day and you leave it on forever, providing that you keep the same cold for all the time. And this is actually the third class of magnet, which are called cryomagnets, which is the most common, the one you see in our lab these days. So what the magnet has a coil in here, and then this coil is actually immersed into a bath of liquid helium. The reason for that is that liquid helium has a temperature of 4 Kelvin, and these 4 Kelvin are below the temperature needed to keep this coil to be a superconductor. So in this condition, this coil, which is usually made by an alloy, like tin and other metals, they are actually being so cold, so this is like 4 Kelvin, is superconductor. So once they install the magnet, they put some current in there, then they detach the cable, there is no current anymore supply, but the current is still in the coil since they have come many years ago, for example. Now, of course, you can lose helium with time, so you have to replenish the helium level to keep the coil immersed all the time. And to make this, so nowadays you can do that every 3 months or maybe even every 6 months, depending on the quality of the magnet. And in order to preserve that as long as possible, what they, of course, the engineer did, they made this can to be a dewar, and then they have another dewar outside, and they fill this other dewar with liquid nitrogen. Liquid nitrogen has a temperature of about 77 Kelvin. So this is a sort of heat shield for the 4 Kelvin. Okay? So why you want to do that? The price of helium is about 5 pounds per liter. The price of this is about 0.2 pounds per liter. So what is going to happen is that almost every week you replenish the liquid nitrogen can, and almost every 3 months or so you replenish the liquid helium can. Okay? So this bit of the instrument is able to make this. What is needed here is you can see actually that so from basic NMR theory, this frequency here is proportional to the field, and actually goes like gamma B0 over 2 pi. So gamma is a constant gyromagnetic ratio, which is proper of the nucleus, and hydrogen is the second highest number, second highest gyromagnetic ratio. And then it's proportional to the field. So the bigger is the field, the bigger is the splitting, and so on. But this also means that if the field changes, this splitting is actually moving. Okay? So if you want to detect this with a sub-Hertz precision, which is very common in NMR, okay, say 0.1 Hertz, Okay, so you want that this frequency, you should be able to detect 0.1 Hertz on this side. Now, this gamma for the hydrogen is something like 263, I don't remember exactly. Time 10 to the 6. So field of the order of 7, 10 Tesla, 15 Tesla are very common in the labs. So let's call it 10 for the time being. And then we have a 2 pi down there. Right. What I wanted to show. Okay, yeah, sorry. I wanted to show which field we want to use. So actually you have the 2 pi here. And then you have the 263 times 10 to the 6 on this side. Okay. And then you have the 10 Tesla here. And this is the kind of differences in field you would like to appreciate. Okay. So as you see, this is of the order of 10 to the minus 7, 10 to the minus 9, 10 to the minus 10. Okay. So this is about it's about 10 to the minus 9 Tesla. Okay. So now we are talking of an instrument, of a field, which is of the order of 10 Tesla, but which is stable within a nanotesla. Okay? Because basically if you have more than a nanotesla, this is actually shifting here, right? By an hertz. So you are not sure, you cannot measure an hertz with precision because this depends on the quality of your field. But current instruments can achieve that. The point is that this kind of design alone will not do that. So you need to add some correcting factors to the main field. And this is called Shim. And I think you are familiar, I don't know if you already started with that. When you sit at the magnet, you start shimming the magnet. Shimming the magnet means basically making it more homogeneous. So the way they do that, they start adding coils all over the place here. Small coils, okay, in different directions. And now you can pump a current through this coil. And this current generates a small magnetic field which adds or subtracts to the main field. And in that way, you basically make it more homogeneous. Okay? So this is the procedure we start with. And this is basically to narrow the dispersion of this line caused by the inhomogeneity of the field. Okay? The second important bit here is actually how to provide the radio frequency. Okay, actually why radio frequency? Sorry. If you take here as an example the gamma of the hydrogen, which I wrote it down here, okay, and you take a field, common field, so you have 263 times 10 to the 6, okay, times 10 Tesla, and then this is divided by 2 pi. This is of the order of hundreds of megahertz. Okay? And this basically means that the frequency we have to use to excite this transition is of the order of hundreds of megahertz, which fall in the region of radio frequency. So now we need a source of radio frequency. Okay? And this again can be made by some electronics, which involves a coil and some capacitor. And all this equipment is contained into another bit, which actually is something that we use to put into the core. And this bit is called probe. And this is actually where you have a coil, and then you have a few electronics. So you have a capacitor here, another capacitor here. So this is a variable capacitor, this is another variable capacitor, and this is an inductance. And here is where the samples sit. Okay? So the probe is the way we can deliver the radio frequency in order to excite the state. And we will see this is also the way we can receive the reply from the states which were excited by our original radio frequency. So why we have this complicated system? Because again, what we need to do again is just to transmit a radio frequency, and to do that we just have to pass a current to the coil. We have two chances to do that. We have to induce some kind of field. Okay, so now you can do it the hard way. You just put a battery or a current and pass through the coil. But in this way, you are going to consume a lot of power, so you need a lot of power to be able to excite that. Or you can do it in the most intelligent way, and which is the way of a tuned, what is called a tuned circuit. So a tuned circuit is a special circuit, which is the one which I wrote in there, which is made by a capacitance, sorry, by an inductance, a capacitance, variable, and then another one. And this piece of hardware has a very special, peculiar things. It's actually, if you put a current through, it actually oscillate. The current oscillate in there, and it oscillate at a frequency which is 1 over square root of LC. Okay, so what is the int there? We need to apply a given frequency. Let's call this exact frequency we want omega 0, for example. So what we can do here, we can build a probe with a fixed coil, so a fixed value for the inductance here, but then a tunable capacitor. Okay? So we put the sample into the coil, and now we have a given energy splitting, so we have to match that with a proper frequency. So how we're going to do that? We just change the capacitance in order to make this omega equal to omega 0. This is the procedure that is known as tuning the probe. The way why you do that, you basically make this circuit to resonate at this exact frequency, which means you can go in with much less power, and then basically this frequency will stay in there and will start oscillating there, and will effectively be very precisely what you want to excite that. The reason of this extra capacitance here is because you want to transmit some power and have almost none reflected back. Okay, so you want to keep all the power you do the most efficient way possible. So you give the power, and the power all stay into the coil. In order to do that, there is another equation which is a bit more complicated, which regulates that. Moving this extra capacitance here, you can make sure that all the power you do, you actually stays into the coil and is not reflected back to the source. Okay? Moving that is called matching the probe. So these are another two very important procedures you always do. You start shimming the magnet to make it very homogeneous, and then you start to tuning and matching the probe, which means making the probe suitable to irradiate at the proper frequency using as less power as possible. Okay? I mean, if you put a lot of power, this eventually generates heating, and this can even eat the sample. And there are serious things. For example, if you are doing some protein study, some protein deteriorate because of the temperature, for example. So you don't want to raise the temperature by the heating of that. So there are it's very important to control the power you are putting into the coil. And this is a trick which allows you to minimize this kind of power. So these are the first two bits of hardware. Now, of course, these things have to talk with us, okay, and eventually end up in a spectrum in a computer. Okay, and this will give us our spectrum. So what the link between here and there is not straightforward, and because now we have still to generate the radio frequency. So this is just a tunable circuit, but we need to irradiate it. I mean, to put the radio frequency in. Once it's in, then we start resonating. Now, to do that, we need what is called a transmitter. So a transmitter is a piece of hardware, which we can put in here. Usually it's called TX. How this is made it's actually made by different parts, in fact. So at the beginning you have what is called a synthesizer. So what the synthesizer does, it just generates an oscillating wave. Okay? This generates a radio frequency. So when I say radio frequency, I mean that the difference between these two peaks is of the order of hundreds of megahertz. Okay? That's the wavelength. Now, this hardware usually generates milliwatt of power, which is far too low. To do NMR, we need hundreds or thousands of watt. So usually between 100 and a kilowatt. Okay? Especially in solid state NMR, we need a lot of power. So this is far too low, by an order of 6. Another important thing is that for some reason that probably you will study, although NMR started in the continuous wave mode, where you actually irradiate at different frequency through the spectrum. Nowadays, what you can do, you can obtain the same result, but just applying a pulse of radio frequency. So what you really want is actually to couple this synthesizer with a gate, which basically is another piece of hardware which opens and closes, okay, and leave it open for some controlled time. So what basically this does, you basically superimpose a gate like that, so opens and closes after a while, and this is of the order of microseconds. And when this is multiplied by our wave function, sorry, our wave, the result is basically something which is 0 here, and then it starts oscillate, and then it's 0 again, right? And this is again of the order of microseconds. Okay? So this gives you a pulse of RF power. But this is still too low. Okay? What you want to do is amplify this signal. And this you can do with an amplifier. So down the road here, you have an amplifier. What comes from the amplifier basically takes this signal, but it actually amplifies a lot. And now this can be of the order of hundreds of watt. Okay? There is just a small bit here. So the problem with amplifiers is that they have fixed gain. So they can multiply your signal by 10, 1,000, 100, or whatever. So this is a fixed gain thing. What if you have to control this fixed gain, because you want to refine that to 110 or 90 or 95 or whatever number. So in order to do that, you put in between an attenuator, which basically, again, this attenuator actually is modulating this to make it a bit bigger or a bit smaller. Okay, again in the millivolt region. And then this is passed to the amplifier, which makes it the big difference. Okay? So for example, if you have 100 of millivolts and you have a gain of 100, then you have 10 watt, right? If you want to scale it by 10, you just scale the attenuator by 10, and then you have the output is 10 times less. So this is the way you control the amplifier, which is always fixed gain. So you cannot change the amplifier gain. Okay? So all these things actually are, so of course the probe has an in and an out. Here is what we put in to excite the states, and here comes out what we should read. So in the in line, we discover that we have an amplifier, and then we have an attenuator, and then we have a gate, and then we have a synthesizer. Okay? So you can imagine that this is basically connected to the computer so that you can control what you are doing to the system. Okay, what about receiving the signal actually? So let's make it more clear. So now we have excited through this line with a computer, we control the synthesizer, we tell him which kind of frequency he has to do, how long the pulse has to be, how much is his power, then we amplify that, put it to the coil, the sample is there, the sample fills the power, and actually we irradiate this transition. So we excite these two states. Once we have finished with that, we have to read what the spins say. So the spins, again, they are magnetic objects. They induce a current into the coil, and this current can be read. The point is that the spins are very tiny magnets, and what they give back is of the order of microwatt. What we give in is of the order of hundreds of watt, or maybe 1,000. Okay? We have to read a very small number there. It's actually, strictly speaking, actually these are microvolt, which you can convert to current. Basically, what you have to do is the power is the current times the voltage. Anyway, you want to read that, and the way to do that is basically to amplify that to some number that you can then treat. So the way to do that is that you feed this signal into another piece of hardware, which is similar to an amplifier, which is usually called pre-amplifier, which basically brings it back to the order of milliwatt, which is something that you can manage with electronics. Okay, we haven't finished there because here we have another problem now. The signal coming out from here is a continuous, it's an analog signal. And of course with computer we can only speak digital, right? So we have somehow to convert this into some digital input. So this is done by what is called an ADC, so analog digital converter. And what this does actually, it basically sample your continuous signal at constant intervals. So suppose you receive a signal from the spins, which is like that. So what this thing is going to do is basically it decides how to sample that. Okay, so this is time, of course. So over time, you have an oscillating system, and you decide actually how to sample with a given interval, which is constant. Okay, something like that. But also, depending on the quality of that, you have to sample in this direction, right? So you also start adding lines in this direction here. So the way this is electronics, they usually talk in bit, and you have like 3 bits, 4 bits, up to 16 or 32 bits ADC converter. So I'm gonna show you a very poor one, which is, for example, a 3-bit converter. A 3-bit means that you basically, any signal, so any bit can be 0 or 1. Since you have 3 of them, you can write things like 0, 0, 0, you can write 0, 1, 0, 0, 0, 1, and so on. There are what? There are 2 to the power of 3 combination, which makes 8. Right? 2 because you can have only 1, 0 or 1, and 3 because there are 3 bits. Okay? So you may have 8 combinations. So a 3-bit ADC will basically divide this into 8. 1, 2, 3, 4, 5, 6, 7, and 8, for example, lines. And what he does now is basically when he receives this point here, so he has to sample at this time. What he does, this point here, okay, is very close to this bit that he knows. I will give you this point instead. Okay? When he comes to sample this bit here, he has to sample this point, which he finds close to this. Okay? And then when he has to sample this, he finds this, which is close to that. So as you can see, I mean, the sampling of the curve will not represent very well the continuous, the analog thing. And how it can be better, basically. It can be better only if we can make this very small and also make many lines here. Okay? So that's why modern instruments, they have ADC of the order of 16 or even 32 bits. A 16-bit has 64 times 124 combination, which is about 65,000 lines. Okay, so it's very good one. I think 32 bits is 4 billion or something, so it's very, very good. So on this side we are somehow safe. What is still missing, what is still causing a little bit of a problem, is that there is a theorem which says if you want to sample very well a wave which has a given frequency or a given lambda, delta, whatever, you have to sample at a frequency which is at least twice as fast as that. Okay? So between these 2 points you want at least another point. Because you can imagine if you have this and then this sampling time is huge, right? So suppose you want to take 1 point here and another point, for example, here. So what you're gonna get is gonna get this point and then you're gonna get this point here. You completely miss what is happening in between. Right? So there is a theorem which is the Nyquist Theorem, which says that if you have a frequency delta, you want to sample at least at 1/2 delta, as fast as that. Okay? What is the frequency in NMR? We are talking that this frequency in NMR, okay, this is the omega 0 we called before, which is of the order of hundreds of megahertz, which is basically 10 to the 8 hertz, and an hertz, remember, is 1/2. Okay? So what you're going to do there is that you want to sample at a time interval which is of the order of 1/2 times 10 to the 8 second, okay, which is of the order of 10 to the minus 8. Okay? Seconds. So it's like 10 nanoseconds, right? So it's far too fast for modern sorry. So this is far too fast. And then what is the trick there again? It's basically to reduce this frequency to something which is manageable. So to do that, you need to insert in this line a mixer. So I'm going to tell you later why I split that into two. So the first thing you want there, before the ADC, so we have the ADC here. and the ADC gives a digital signal which is then represented as a spectrum, we need a mixer. Why this what a mixer does? It's actually another piece of electronic which basically takes two frequencies in omega 1 and omega 2 and gives back two frequencies, but gives back the sum and the difference. Okay? So now suppose that from the spins comes something like 100 megahertz and, I don't know, 20 kilohertz. Right? Now you mix it with a reference signal, which is 100 megahertz. What is going to come out from the mix is the sum, which is like 220 meg and 20,000 hertz, or only the 20,000 hertz, right? So 20 kilohertz, right? So what you can basically do here, you add another small piece of hardware, which is called a low pass filter, which is basically selects everything which is, for example, below 1 megahertz or something like that. Okay, this will basically draw out this signal and allow only the 20 megahertz. So whatever passes through here is is below 1 megahertz. So in this particular case, is of the order of 20 kilohertz. Okay, what this changed? What is this changing, basically? Is that now our oscillatory wave is of the order of kilohertz. Okay, so 10 to the minus 5 seconds. Now we have to sample at a different region, so much slower. And there is hardware to do that. Okay? We have almost finished with the pieces, but there is an important concept here, which explains why we have these two mixers. Actually, we need to make two mixers, and this is the concept of quadrature detection. So what is going to happen here is that since we have a reference frequency at 1,100 megahertz, for example, so now our signal can come plus 20 megahertz or minus 20 megahertz, right? And they are both. They can be both real. I mean, we have to distinguish which is the real. What is the sample actually producing, right? So it's very important to discriminate if it's plus or minus. Okay. So in order to do that, we have to add a little bit of more sophistication. And so the reason why is that the signal we read actually has, well, it's a constant, then it has some oscillatory nature. Okay, so oscillate some 2 pi omega 0 t, and also is damped. Let's see. Yeah, actually it's better than mine. Like this. So basically this is a signal which is, it's actually an imaginary signal because there is the eye here. So you remember this is actually, this can be simplified in cosine of omega t plus I sine of omega t. Okay, that's Euler equation. And it's damped by an exponential decay. So in fact, this is what we got a free induction decay, which is what we observe before the spectrum. So this function is basically the multiplication of an oscillating wave, which is damped because the signal decays with time, so damped by an exponential, and the product of that is something which actually goes like this. So basically oscillate, but at the same time decays with time. And this is what is called a free induction decay. Okay? The Fourier transform of this gives you a peak. So this is time. The Fourier transform changed into a frequency domain. So now these are like frequency. And this is basically your omega 0 returned. Okay, if the sample has more frequencies, then you get more peaks, and you can understand all the characteristic frequency of the spins you have in the system. And then from there you can work out, for example, molecular structure, property of the material, and things like that. Okay, but this is the first thing, is what we are talking about, how we detect this spectrum. And in fact, what we really digitize here is this free induction decay. Okay? So now, what we want to do here is, when we go through a filter, what happens is that we multiply this signal. So when we go through a mixer, we multiply this with some reference frequency. Okay? And what this gives you is basically cosine. So for simplicity, suppose that we have only real signal, so we only have this part, just to simplify things, okay? So this will give you cosine theta t, or omega t, cosine reference frequency t. So this is the product of two cosines, and this can be also expressed like sorry, actually I need that. Sorry. So this can be expressed like the cosine of the sum minus the cosine of the difference. Okay, that's why we get the from the mixer out. We got plus and the minus of the frequency, and then this goes to a filter, and we take, for example, only that. So only we take the cosine of omega minus omega f t. Okay? So now what we would like to do is to take a 90-degree shifted signal, which is the quadrature of that. In order to do that, the way to do that could be mathematically just taking this multiplied by the sine of omega f t. Why is that? Because in this case we have cosine omega t sine omega f t. I'm going to check to get the signs right. Plus and plus, I guess, whatever. So this will give you the sine of the sum. I'm not sure about these signs there. The sign of the difference. So again, if you go through a low pass filter, we only retain this bit here. So why you do that? Because now you have the cosine and the sine. So you have the signal taken at exactly 0 degree, let's say, and 90 degree phase shifted from that. This corresponds like if you are in a plane and you have your x and y, you are going to detect fictionally you have a coil along x and a coil along y, okay? And then you detect this here and this there. Okay? That's why it's called quadrature detection, basically. So in the probe you only have one coil, okay? And the coil actually makes a field in the x direction. Nominal x direction, okay? In the plane. So usually in this, when you discuss NMR, you assume that the z direction is the direction of the main field, B0. Okay? So the transfer plane, you have a coil. So in order to get both signal, you don't really need to have another coil along y, which is actually very difficult, very tricky to do it, because basically you will have two coils at the same time in there, and once you pass a current through one coil, it's very difficult to isolate the other one. So this will affect the other coil immediately, okay, because of Maxwell law. So basically, this geometry is very hard to make, but you can basically overcome this problem just making mixing once with a signal and then which oscillates as a cosine, and once with a signal which oscillates 90 degree out of phase, which means just the sine, because sine and cosine are 90 degree out of phase. So what you actually have from the computer, we have a reference signal. Okay, this is the omega. This is a frequency, so let's call it Ni RF. This goes straight in this mixer, but it goes in a phase shifter, and this phase shifter goes in that mixer, and this phase shift is like 90 degree phase shift. Okay, so basically the computer gives you a reference which is of the order of hundreds of megahertz, and this is mixed here, because remember in the mixer you need two things. You need your signal, which is again of the order of hundreds of megahertz plus or minus some kilohertz or hertz or whatever it is, with a reference. And now you split this circuit in two, and one of this mixer is preceded by a 90 degree phase shift in order to be able to implement what is called a quadrature detection. So which means physically it's like we take the signal from the two things. So in this way we are able to understand if a frequency is actually positive or negative. Because if you have a single coil, you cannot distinguish if this is rotating like that or is rotating actually like this. If you can detect two components of it, you can do that. Okay, that's why you would like to do that. So all this bit of electronics here are actually contained in what is called the NMR console. And while the amplifier and the preamp usually stands outside of the console. This is for practical reason actually. The amplifiers are very huge. It's a piece of equipment. It's a big piece of equipment which stands by its own. And usually you need like cooling power, because this generates a lot of heat. You would like to remove this heat from the room, and also lots of noise. The preamp actually is placed as much as possible close to the probe, because basically what you're going to detect is a microvolt in a cable, but the cable there are electrons and there is some thermal noise. Okay, so the electron actually moving because of thermal noise, and this is actually a current, right? So you actually are going to detect also this noise, and this will make the noise in your spectrum. Okay, so what you want to do is to minimize this process, so you get the preamp very close here in order to not get a lot of dispersion of this very small signal. Once you have amplified this in the order of milliwatt, this is a much more manageable, much bigger, let's say, electronically speaking, signal that you can handle later on in the console. So when we go down in the room, I mean, we are going to see all these pieces. Usually, it's not very clear to see these things because these are usually integrated circuits, so they are like circuit boards, like in the computer. So I can show you the board where it is and so on, what it does, but again, we cannot really look how this particular mixer is made of, because it's made by small integrated circuits. We can clearly see the preamp, the amplifier, the probe, and then things like that. And basically, this is the basic of it is done. And so we have built a spectrometer in here, saving about $1 million, $1.5 million, which is the price of the modern. Yeah, spectrometer. Any question you want to think about and ask later in the lab, or you won't actually have time? We can go in the lab now and look at that. You would like that?